Let us continue by considering mappings between sets. A mapping F from a set A to B is a way of associating each element A in A with its image f of A within B. The set A is often called the domain of the mapping, and B is called the range in this book, but is more often called the codomain. In particular, you also have that the set of all elements f of A is more usually called the range or the image of the mapping F. A mapping is said to be injective if the outputs are unequal whenever the inputs are unequal, or conversely, if the inputs are equal, then the outputs must be equal. A mapping is said to be surjective if for every B there is an A such that B is equal to f of A, and it is bijective if it is both injective and surjective. A bijective mapping in this way is said to establish a one-to-one correspondence between the sets A and B, since it associates to each point A a unique point B, and each point of B is associated in this way to a unique point of A. A mapping F from A to B is bijective if and only if there's a mapping G from B to A, such that G of F of A is equal to A for every A in A, and likewise that F of G of B is equal to B for every B in B. Indeed, if F is bijective, then by definition must be surjective, so each point B in big B is the image B equals f of A of a point A in A. However, since F is also injective, the point A is uniquely determined by B, and consequently can be viewed as the image A is equal to G of B of another well-defined mapping, G from B to A, for which B is equal to F of G of B. That is, this mapping G is one that says we have, by definition, found a point A and B that are matched together, so G is the one that associates A with the point B in this way. Given that we have B is equal to F of G of B, and additionally we now have that for any A in A, then if we substitute B is equal to F of A in the preceding formula, then we know that F of A is equal to F of G of F of A. So since F is objective, it follows that A is equal to G of F of A. So we have a well-defined function, G, that obeys the rules we want it to. Conversely, if there's a mapping G from B to A, such that G of F of A is equal to A for every A in A, and F of G of B is equal to B for every B in B, then the mapping F is clearly both injective and surjective, so it must be bijective. This mapping G that we constructed is called the inverse mapping to F, and it's usually denoted that G is equal to F inverse. And also, clearly, we have that it's a bijective mapping from B to A. In general, though, for any mapping, there can be associated to any subset. X is a subset of the domain A. You can have its image, f of x, which is a subset of B, defined that f of x is equal to the set of all f of a's within the codomain B, such that A is an element of X. So for any element A within X, you consider its image under F, and the set of all of those images is the set f of X. Likewise, you can define an inverse image, f inverse of Y, which is going to be a subset of A, where Y is a subset of B, the codomain, which is defined as the set of all elements within A, who serves the preimage of some element in Y. The image f of x may or may not coincide with the range of the mapping of f. If f is injective, then clearly this determines a bijective mapping from any subset x is a subset of A to its image f of x. That is, consider any element x. By f it is mapped to one point since it is injective. Therefore, we have a bijection from that corresponding point to a original point. If f from A to B is bijective, the inverse image f inverse of y is of a subset y is a subset of B is just the image of that subset under the inverse mapping f inverse. It should be kept in mind, though, that f inverse of y is well defined even for mappings f from A to B that are not bijective, so mappings for which the inverse function is not defined. For instance, you can consider y is equal to x squared, and consider the inverse image of, you can consider the pre-image of a set like 1. And the pre-image of the set 1 is the set 1 and negative 1. It may be worthwhile to figure out why that makes sense, but pre-images are well defined even for non-bijective sets. And thus the notation we are using here is a little confusing, so you should be careful considering whether or not f inverse represents the inverse function or the pre-image, the inverse image of a set. And from all of this, we see that there are some rules that images and pre-images follow, such that for any mapping f from A to B, and any subsets x1, x2, which are subsets of the domain, and y1 and y2 that are subsets of the codomain, you can see that the image of unions is a union of images. The image of intersections is a subset of the intersection of images, but this in particular could be proper. However, pre-images are more well behaved in the sense that the pre-image of a union is a union of pre-images, and the pre-image of intersections is an intersection of pre-images. This is a question to be proved later. As noted, this is an instance in which the inverse images of sets are better behaved than the images of sets. And now we can continue by considering composite mappings and then going on to the power set of sets. So to any pair of mappings from f from A to B and g from B to C, you can associate the composite mapping g of f, which goes from A to C, defined by g of f of A is equal to g of f of A for all A and A. The order in which this is taken is important, and g of f means first applying the mapping f and then the mapping g. From here, to any set A, there can be associated other sets. For instance, the set consisting of all subsets of A, which is called the power set of A, and denoted by P of A. The power set of the empty set is a set that contains a single element, since the only subset of the empty set is the empty set itself. However, the power set of a set containing one element has 2 elements, namely the set itself containing that one element and the empty set. From here, we see that the power set of a set containing 2 elements has 4 elements, namely the empty set, either one of the elements, or the set containing both elements. In general, we note that this follows the rule that 2 to the number of elements within a set, if that's well defined, is the number of elements in the power set. This will come up later. However, additionally, we can consider the set of mappings between any two sets. Namely, between any two sets A and B, you can associate the set of mappings B to the A, which is the set of all mappings F from A to B. If, for instance, A consists of a single point, then there's the natural bijection from the mapping F, a natural bijection phi, between the set of all mappings between that single element and the set B to the set in total B that associates to any mapping in this domain of phi, B of A, its image F of A and B. So, to describe that in more detail, we note that any element in this set is a mapping F that sends A to some element of B, namely F of A. However, each of those is uniquely defined since the set of the element A has exactly one element. So, since this mapping is, there's not really any other way to define it, we can consider that whatever images exist that are called F of A within B, we simply associate those images with the mapping themselves. Since, as is noted, the mapping F is fully determined by its image and any point B in B. So, because any point B in B, this is B to the A is the set of all mappings, then it must be the point that there must be a point B such that is the image of some mapping F for which F of A is equal to B. Likewise, we can do the reverse. We consider all the mappings from B to A, and then from B to A, namely this set, are going to associate to each of those mappings an element within A. Since there's a single mapping between B and just the set of A, the mapping for which A is equal to F of B for every B. So that singular mapping, that's an element of this set, is associated with element A in this set. If instead we have a slightly more complicated case, in which B is the field of two elements, namely the set of 0 and 1, there's a natural bijection phi between the field of two elements, the set of mappings from A to the field of two elements, and the power set of A. This is where our previous note will come in handy. That associates to each mapping F from A to the field of two elements a certain subset, E sub F, that is the pre-image of the set 1, which is a subset of A. So, this is because the mapping F is determined uniquely by the subset E sub F of A, E sub F, which is a subset of A, since for any x in that set, it is the case that f of x is equal to 1, and f of x equals 0 for every other element. One way of thinking about that is choose some elements within your set A that you will send to 1, and the rest of the elements will be sent to 0. This uniquely determines a map F. Therefore, you can associate that function with that subset you chose that is a subset of A, or namely the subset that you send to 1 under this mapping. And that subset is an element of the power set of A, so you have a bijection. Namely, whatever subset you chose originally is clearly a power set and is associated with exactly one mapping within A to the field of two elements. Therefore, you have a bijection. Since these are uniquely defined, they are uniquely determined. We can make this a little more rigorous by introducing the idea of a characteristic function, chi of E, which is a function that's defined on any subset E is a subset of A, such that chi of E from A to the field of two elements is defined by chi E of a point A is 1 if A is in that subset, and 0 if A is not in that subset. And has the property that the pre-image of 1 under chi of E is namely the set E itself. This bijective mapping, which comes up naturally, is a way of associating a power set with the set of mappings from A to the set of two elements. And because the set of two elements has two elements, we sometimes denote with a 2. So the power set of a set A is sometimes denoted by this. Where this side, however, note that this equality is just meaning that there's a bijection between them, and they are not the same sets. For instance, the reason why this is because the power set of A is the set of all subsets. Meanwhile, this symbol on the right represents the set of all mappings from A to the set of two elements. And while there's a natural bijection between them, choosing subsets of A to be sent to 1 is the same thing as choosing a subset of A, so it's an element of the power set. This is a set of functions, and this is a set of sets. So they cannot be equal. But, as we noted, there is a very clear bijective mapping between them. Thank you.